Hello students. In this class, I'll be teaching you about another type of group called as the permutation group. So for that, we consider a set S is equal to 1, 2, 3, and I define a function f from S to S to be 1, 1 and odd 2. So let us look at what are these functions f. Now, when I take a set S is equal to 1, 2, 3, I take the elements 1, 2, 3 to be the vertices of a triangle. So when I take the first function f1, that means 1 is mapped to 1, 2 is mapped to 2, and 3 is mapped to 3. So this kind of function, I'll write it in this form. That is 1 is mapped to 1, 2 is mapped to 2, and 3 is mapped to 3. So this I consider to be the first function. So to get the second function, what I do is I rotate this triangle in an anti-clockwise direction. So 1 takes the position of 2, 2 takes the position of 3, and 3 goes to 1. So that is what I'm writing as a function 2 here. So 1 goes to 2, 2 goes to 3, and 3 goes to 1. This is one rotation. So this is called as a rotation here. So this I consider it as the second function f2. Next, the third function f3, I'll write it as this 1 is in the third position now. So 1 is mapped to 3, 2 is mapped to 1, and 3 is mapped to 2. 3 takes 2's position, 1 takes 3's position, 2 takes 1's position, and 3 takes 2's position. So this is another rotation. So F3 will be 1 goes to 3, 1 goes to third position, 2 goes to first position, and 3 goes to second position. This is F3. This is another rotation of this triangle. So you have got F1, F2 and F3. Next, one more function where I can obtain is I can keep 1 as it is. I fix the position of 1 and I only change the position of 2 and 3. That means about this point 1, 2 and 3 are reflected. So 2 goes to third position and 3 goes to second position. So I can write this F4 as 1 goes to 1, 2 goes to 3, 3 goes to 2. Similarly, F5 will be, I'm fixing 2 now. 2 is fixed, 2 is mapped to 2, 1 is mapped to 3, 3 is mapped to 1. So this is F5. And the F6 will be, I fix third position. So 1 is mapped to 2 and 2 is mapped to 1. So these are called as the reflections. So you have the rotations and the reflections, and no more functions are possible. So all these functions are 1, 1 and also onto, because every element in S is mapped to unique, has a pre-image. So these are the functions F1, F2, F3, F4, F5 and F6, and these functions form the symmetric set, and that is denoted as S3. So S3 has 6 elements. So when we look at this, the number of elements in a symmetric set will always be, in this case, since S3 has 3 elements, since S has 3 elements, S3 will have 3 factorial elements. Similarly, in general, if S has n elements, then Sn will have n factorial elements, and these F1, F2, all F1 to F6 are called as permutations. So what are these permutations? Let us see now. A 1-1 mapping of a given finite set, non-empty set S of n distinct elements to itself is called as a permutation of element n. So if you have a mapping F from S to S, and if it is of same order, if it is of some order n, then that is, and it is a 1-1 mapping, then it is called as a permutation. Always remember, whenever you have a 1-1 function from a finite set to itself, then it will definitely be a onto function. So that is what it says here. If S is a finite set containing n elements, then the set Sn of all permutations of S is called a symmetric set, and it is denoted as Sn. It contains n factorial elements, as I explained in this example. S3, you have 3 factorial, that is 6 elements. Similarly, you can do the same thing for S4 also, where S4 is nothing but S is a set containing 4 elements, that is 1, 2, 3 and 4. Then you can take, in here we took, there are 3 elements, so I took a triangle. Then you can take a square and find out the rotations and the reflections. So you will get 4 factorial, that is 24 elements. Okay. Next, let us look at what is equality of two permutations. So I have taken two functions here. So two elements of which are permutations, that is f and g. And to check whether these two permutations are same, that is to check that the element should be mapped to the same element. So here you have A is mapped to B is mapped to C, and C is mapped to A. Here also B is mapped to C, A is mapped to B, and C is mapped to A. Only the order is changed, but the mappings are the same. Since the mappings are the same, you call these two permutations as equal. So A is mapped to B, here also A is mapped to B is mapped to C, here also B is mapped to C is mapped to A, and here also C is mapped to A. So in this case, it is called as equality of two permutations. So F is equal to G. And the identity permutation is if the elements are mapped to itself, then that kind of a function is called as that kind of a permutation is called as an identity permutation. So in this case, F1 is called as the identity permutation because 1 is mapped to 1, 2 is mapped to 2, and 3 is mapped to 3. This is an identity permutation. Next, let us look at the composite of permutation. That is nothing but product. So you don't multiply directly in case of permutations. You call this as a composite of permutations. So I'll explain what is a composite mappings. Let F and G be two permutations defined on a set S of degree n. The composite mappings G circle F. We denote composite mappings in the form of G circle F and F circle G. So are defined by G circle F of x is equal to G of F of x for all x belonging to S. So you have a function F from A to B and G is a function from B to C. Then upon element x is mapped to element F of x through F, and this element F of x, so elements of B is of this form, so it is of the form F of x, and this G takes an element F of x to C in the form of G of F of x, and we denote that as G composition F. So G composition F is nothing, you operate F of x first and then operate G. So G of F of x. So G composition F is equal to G of F of x. So G composition F of x is equal to G of F of x for all x belonging to S, and F composition G of x is equal to F of G of x for all x belonging to S. So now let us look at how do we take the product of two permutations. So here I have the set S is equal to 1, 2, 3 and 4, and F is one permutation and G is another permutation. Now we need to find F composition G and G composition F. This is very important in case of exam point of view. So you should know this. F composition G is, write the permutation F first and then G. So we need to find out what is F composition G. So what is F composition G? F composition G is F of G of x. So you first operate G and then you operate F. For that, we first find out, we go from right to left here. Now here you have this composition. The first row will always be equal to 1, 2, 3 and 4 itself. Okay. The first row is, the first row is 1, 2, 3, 4. So write the 1, 2, 3, 4 as it is in the first row. And here you first operate G. So 1 is mapped to 3, and you take here 3 is mapped to 4. So you write it as 1 is mapped to 4. Next, 2 is mapped to 1. Here 1 is mapped to 2. So 2 will be mapped to 2. Next, 3 is mapped to 4 and 4 is mapped to 1. So I can write it as 3 is mapped to 1. Next, 4 is mapped to 2 and 2 is mapped to 3. Therefore, 4 is mapped to 3. This is a easier way to find out F composition G. You can as well do it in a other method and writing explicitly what is f of 1, f of 2, f of 3, f of 4, and g of 1, g of 2, g of 3, g of 4, and then finding out F composition G. You will get the same answer, but it takes a longer time. So instead you can do this way. So now I'll explain again what is G composition F. So write G composition F as write G function first and then F. So here we go from right to left again. So 1 is mapped to 2 and 2 is mapped to 1. So you have 1 is mapped to 1. Next, 2 is mapped to 3 and 3 is mapped to 4. So you have 2 is mapped to 4. Next, 3 is mapped to 4 and 4 is mapped to 2. So you have 3 is mapped to 2. 4 is mapped to 1 and 1 is mapped to 3. So you have 4 is mapped to 3. So this is how you find out F composition G as well as G composition F. Next, we look at what is an inverse of a permutation. See, since F is a permutation and it is 1, 1 and onto, therefore its inverse definitely exists. That is a condition for an inverse to exist. The function has to be both 1, 1 as well as onto. And since inverse exists, to find the inverse, what we do is we interchange the rows of the permutation. See, for example, you had taken F2. I had explained this uh, F2. F2 is 1, 2, 3, 2, 3, 1. So this will be F2 is equal to 1, 2, 3, 2, 3, 1. So F2 inverse, what I do is I just interchange the rows here. So I'll write the first row as 2, 3, 1 and the second row as 1, 2, 3. Now I'll rewrite this as 1 comes first. So I'll write it as 1, 3 first, then 2, 1, then 3, 2. This is nothing but the element F3. So we get this as F2 inverse is equal to F3. So when we look at this set S3, this set S3 forms a group under composite multiplication. Composition under composition, this set S3 forms a group. Similarly, you can find the inverse of F4, F5 as well as F6 using the same method. So we have a theorem which states that let S be a finite set containing n distinct elements, then the symmetric set of all permutations of degree n on S forms a finite group of order n factorial with respect to composite of permutations as the composition. So you don't have to look into the proof of this. You just know that this, and if you have to do it also, it is very easy to find out. You need to just check all the four conditions, that is closure, associative, existence of identity, and existence of inverse. Since I've already told that the identity element exists for every Sn, you can easily know what is an identity element of this Sn in general, and check all the four conditions. So this Sn forms a group under composition. Now let us look at the next theorem, that is the Kaylees theorem, which says that every finite group is isomorphic to a permutation group. It can be either isomorphic to a permutation group or a subgroup of a permutation group. Now you have this, okay, and when you take this permutation group S3, this is a permutation group S3, it is the smallest group which is non-abelian. Any group of order less than or equal to 5, it is always abelian, and this S3 is the first smallest group which is a non-abelian group. And you would have got a doubt saying every finite group is isomorphic to a permutation group. But Z6 is not isomorphic to S3. But Z6 will be isomorphic to some subgroup of a permutation group. That is what Kaylees theorem says. And whenever I say isomorphic, that means all these group, if you have two groups G and G dash, and if I say that G and G dash are isomorphic, that means all the properties of G are satisfied by G dash as well. So if you have an order of A is some say 5, then order of f of A will also be equal to 5 itself. So then we say that to be isomorphic. So here Kaylees theorem says that every finite group is isomorphic to a permutation group, or we can also say it as every finite group is isomorphic to a subgroup of a permutation group. If permutation group is a non-abelian group, but a subgroup of it can be an abelian group. You can take an example of S3 and find out its subgroups and show that it is abelian. You can do it as an exercise. So let us look at this proof. This is a very important theorem. Every finite group is isomorphic to a permutation group. So I consider let G comma star be a finite group of order n. For all A belonging to G, consider the mapping. So for every A in G, I consider a mapping Fa is equal to G to G defined by Fa of x is equal to A star x. Since for every A in G, I have assigned Fa, so there are as many mappings of F as the order of n here, as the order of G. So how many elements of G are there? Those many mappings I can form with this kind of mapping. Fa from G to G defined by Fa of x is equal to A star x for all x belonging to G. Then Fa is 1, 1. The reason is Fa of x is equal to Fa of y if I consider. This is nothing but A star x is equal to A star y. Then by left cancellation law, I get this as x is equal to y. Since both these groups are of order n and it is 1, 1, that means to say that it will definitely be a onto function. So since it is both 1, 1 and onto, these mappings Fa are called as the permutation. That is what the definition of permutation says. That is, if you have a mapping which is both 1, 1 and onto, that is called as a permutation. Now I consider all these permutations Fa where A belong for all A belonging to G, and I form that as a group called as G dash. So G dash is equal to all those Fa such that A belonging to G. So here you have the order of G the same as order of G dash. So whenever you have to check that it is isomorphic, that means that order of G, if you have a function f from G to G dash and it is isomorphic, f is isomorphic, that means that order of G is same as order of G dash. So I have taken from G, I have formed these permutations Fa, and all these Fa permutations I combine and write it as G dash. Now I define one more map. You need to prove that this G is isomorphic to G dash. This is all the this is called as a permutation group because it has all permutations. Now to um, check whether this G and G dash are isomorphic, we define a mapping. Define a map phi from G to G dash by phi of A. Elements of G are of the form A, B, C, and so on for all A belonging to G. So phi of A is equal to elements of G dash is of the form Fa. So I'm assigning the mapping phi of A is equal to Fa for all A belonging to G. Now, to show that it is isomorphism, it has to satisfy three conditions. That is, phi is 1, 1, onto, and homomorphism. So let us first check phi is a 1, 1 function. For that, we have phi of A is equal to phi of B. This implies that Fa is equal to Fb from the definition. This is equal to Fa of x is equal to Fb of x for all x belonging to G. Now we know the definition of Fa of x, that is A star x, that is equal to B star x. By right cancellation law, we have this as A is equal to B. Since Phi is 1, 1, and I already told you that both G and G dash are of same order. So since Phi is 1, 1, therefore we can conclude saying that Phi is also onto. Next, we need to check that Phi is a homomorphism. That means phi of A star B is equal to, from the definition we have it as f of A star B, or I can write this as f of A star B of x is equal to A star B star of x. And you know that G is a group, so it satisfies associative law. So I can write this as A star of B star x, and A star of B star x can be written as f of Fa of B star x, because A star x is defined as Fa of x. So A star of B star x can be written as Fa of B star x. This is equal to Fa of Fb of x from the definition. So this is equal to Fa Fb of x. We are changing the brackets. Therefore, we have come to a conclusion saying that Fa star b is equal to Fa Fb. Hence, phi of A star b is equal to f of A star b is nothing but phi of A star b, and Fa is equal to phi A, and Fb is equal to phi b. Therefore, we have shown that phi is 1 1 onto and homomorphism. Therefore, phi is an isomorphism from G to G dash, and therefore we write it as G is isomorphic to G dash. So every finite group is isomorphic to a permutation group. Thank you.